This module is about the composition of the atmosphere. The Earth's atmosphere is what you will learn about in this module, and you will also get to know the composition of the atmosphere, how the composition changes with altitude, what are the different chemical species present in all the parts of the atmosphere, the effect of certain species such as particles, ions and radicals present in the atmosphere. You will also be able to differentiate between air and atmosphere. You will know the composition of atmosphere, how it varies, and how the temperature, pressure and light penetration varies in different sections of the atmosphere. The atmosphere for any planet is a blanket of gases surrounding the planet which is held in place by gravity. So for Earth it is air which is there present in the atmosphere, but all the atmospheres of planets in the solar system are not same. However, there are some similarities in groups of planets. For example, the 4 innermost planets, which are also called terrestrial planets, Mercury, Venus, Earth and Mars, have some similarities, and the other group of planets, the 4 outer planets, Jupiter, Saturn, Uranus and Neptune, also have some similarities in their atmosphere. The terrestrial planets have heavier gases such as nitrogen, carbon dioxide, oxygen, ozone, etc. And the gas giant planets, as the outer planets are often called, have atmospheres comprised mostly of hydrogen and helium. So the Earth's atmosphere, as we already said, is made up of air. Air is a mixture of gases. The major components of air are nitrogen and oxygen. There are some minor constituents such as argon and some which are trace constituents, which are the other noble gases, and carbon dioxide. This is, we are talking so far about dry air. There could also be wet air in which there is water vapor. Water vapor, of course, is not present in the same amount all over the globe, and it varies from 0 to 2%. So average of 2% we can say is composition of water vapor in the atmosphere. Constitution of the atmosphere is not the same as we go up with altitude. There is a layering of the atmosphere. We have 4 principal layers of the atmosphere. The lowermost layer, which extends to about 15 kilometers above the surface of the Earth, is called the troposphere. The second layer just above that, which extends to around 50 kilometers above sea level, is the stratosphere. Above that is the mesosphere, which extends to 85 kilometers, and the outermost layer is the thermosphere, which extends to 500 kilometers above sea level. The composition of each of these layers is different. The troposphere has, as we already said, nitrogen, oxygen, argon, carbon dioxide and water vapor. The stratosphere has nitrogen and oxygen and also ozone. The ozone layer is a part of the stratosphere. And above that is the mesosphere, where in addition to molecular nitrogen and oxygen, there is also nitrosyl ion and nitrogen and oxygen molecule ions. And beyond that, in the thermosphere, there are again ions such as the oxygen molecule ion, the oxygen atomic ion, nitrogen, nitrosyl ion and the nitrogen molecule ion. So just like the chemical species are different in the different layers of the atmosphere, temperature change with altitude is also different in each layer of the atmosphere. In the troposphere, the temperature decreases with altitude. So at the outermost layer of the troposphere, which is called the tropopause, the difference between the troposphere and the stratosphere, at the tropopause the temperature is minus 56 degrees Celsius. So from an average surface temperature of about 15 degrees Celsius, we move to minus 56 degrees Celsius at the top of the troposphere. So that becomes a decrease at the rate of 6.4 degrees Celsius per kilometer of altitude. That is called the normal environmental lapse rate. Beyond that, in the stratosphere, the slope of the temperature altitude curve becomes positive. That is, there is an increase of temperature with altitude. At the topmost layer of the stratosphere, which is around 50 kilometers from the surface of the earth, as we already said, the temperature becomes minus 2 degrees Celsius. So, the lapse rate, which we have mentioned earlier, is a word signifying the slope of the temperature altitude curve. As we've seen in the troposphere, the lapse rate is negative, and in the stratosphere it is positive because the temperature increases. In the mesosphere, the temperature decreases again till at the top of the mesosphere the temperature becomes minus 92 degrees Celsius. In the outermost layer, that is the thermosphere, the temperature increases and it goes up to as high as 1200 degrees Celsius at the top of the thermosphere. The troposphere is characterized by turbulence. This is because there are air masses moving around, and that is what gives a place its weather, the movement of air masses, and along with that water vapor. In the stratosphere, the turbulence is much lower because the stratosphere doesn't have that much of movement since it is not in contact with the surface of the earth. In the mesosphere, there are many ions, and these ions help in radio transmission. As we already know that the ionosphere extends beyond 50 kilometers to the end of the atmosphere. The ionosphere is known to be helpful to human civilization because it aids radio transmission, and this happens because radio waves reflect from the surface of ions and go to their destination wherever they are intended to go. And radio transmission is better at night because there's a lift in the bottom layer of the ionosphere. That is, the ionosphere is at a higher altitude at night than in the daytime. This happens because when there is no UV light from the sun, the ions slowly recombine, and the recombination is more in the denser troposphere. The stratosphere and mesosphere are more rarefied, that is, the density is lower, and so the ions recombine more slowly. The bottom of the ionosphere lifts up at night, and we get further radio transmissions at night. The stratosphere is important to us because of the ozone layer. At the top layer of the stratosphere, ozone is formed all the time because of combination of oxygen molecule with oxygen atoms, which are subsequently formed from oxygen molecule. That is, oxygen molecules first dissociate due to radiation into two oxygen atoms, and then each of these oxygen atoms combines with the oxygen molecule to give two molecules of ozone. So ozone is getting formed, but on the other hand, ozone also gets destroyed in the stratosphere, which is a natural process. It absorbs light and then gets reconverted into oxygen molecule and oxygen atom. But these two phenomena balance each other, and there is a steady state of ozone concentration in the stratosphere as long as there is no human interference. However, lately in the last few decades, it's been seen that the ozone layer is thinning due to human interference, and we will come to that when we discuss the ozone depletion. Particulate matter is a very important constituent of the atmosphere. Particulate matter is made up of tiny particles, that these are tiny pieces of solid and liquid matter present in the atmosphere. The number of particles per unit volume of air can vary from several hundred per cubic centimeter in purer air to more than 105 per cubic centimeter in polluted air. And the sizes of these particles range from 0.1 to 10 micrometers. Particulate mass level can range from 10 microgram per cubic meter in cleaner air to 60 to 2000 microgram per cubic meter in polluted urban areas. Colloidal sized solid and liquid particles present in the Earth's atmosphere are known as aerosols. Particles of natural origin with diameter less than 0.2 micron are called Aitken particles or Aitken nuclei. This is after a pioneer of aerosol science, John Aitken. The sources of aerosols define their composition. Wind-blown mineral dust comes from mineral oxides and other material blown from the Earth's crust. This particulate is light absorbing. The second largest contributor of global aerosol is sea salt, coming from sea spray, and consists mainly of sodium chloride originating directly from the ocean. Other constituents of atmospheric sea salt reflect the composition of sea water, and thus they can be found exactly like that in the ocean. They can contain magnesium sulfate, calcium, potassium, etc. Sea spray aerosols contain both inorganic as well as organic compounds which alter their chemistry. Particles which occur naturally in the atmosphere are bacteria, fog, pollen and volcanic ash. The size and chemical nature of particles are very important because this can influence how the particle interacts with humans and other life forms. Formation of particulate matter can be due to several things that happen. For example, metal oxides are a major group of inorganic particles in the atmosphere. They originate from the combustion of fuels. Iron oxide particles, for example, originate from the combustion of pyrite containing coal. Calcium oxide particles come from coal combustion also, because there is some calcium carbonate in the ash fraction of coal, which is then converted to calcium oxide and discharged through the chimney stack. Aerosol mists arise from sulfuric acid obtained by oxidation of sulfur dioxide, which catches vapor to form small liquid droplets. Once sulfur dioxide becomes sulfur trioxide in the atmosphere, it further combines with water to directly give sulfuric acid. In the presence of basic air pollutants such as ammonia or calcium oxide, salts can be formed like ammonium sulfate and calcium sulfate. These are also in the form of solid aerosols. Automobiles can be a contributor to lead particles in the atmosphere. Lead or lead halide is discharged from the automobile exhausts, and this happens because leaded gasoline is used as fuel. Elements which can be introduced by human activities such as metallurgy and metal processing can include barium, lead, manganese, calcium, copper, vanadium, zinc, magnesium, iron, etc. And elements which can also come from natural sources, particularly terrestrial dust and sea salt, are potassium, sodium, aluminium, silicon, chlorine, iron, etc. In addition to inorganic particulate matter, there can also be organic particulate matter. This is obtained from a number of sources. There could be emission from vegetation. There could also be emission from automobiles because of combustion of hydrocarbon fuels. From a study conducted in the US on 200 air samples, it was concluded that the average formula for the organic particulate matter is C32H48O3.8 S0.083 X 0.06, X being a halogen, could be chlorine or bromine, and the size of these particles could range up to 1 micron. Such particulate matter is a potential health hazard. One class of components of organic particulate matter, polycyclic aromatic hydrocarbons PAH, have been in the news a lot recently since these have carcinogenic properties. They are commonly found in the upper atmosphere at about 20 microgram per cubic meter level. They originate from pyrolysis of higher paraffins present in fuels and plant material, for example from forest fires. High molecular weight compounds are pyrolyzed during combustion to yield lower moleculate ones, which then undergo further pyrolysis and to give aromatic hydrocarbons, including polyaromatic hydrocarbons. The polyaromatic hydrocarbon compounds are usually adsorbed on soot particles, which are also formed during combustion. In urban areas, this accounts for half of the total particulate load. The hydrogen content of soot is 1 to 3% and the oxygen content about 5 to 10% due to partial surface oxidation. Soot acts as a carrier for toxic inorganics due to its large surface area. The size range of these particles is between 0.1 to 20 microns. Physical and chemical properties of particulate matter are very important. For example, the size and shape. And for odd shaped particles, the particle size can refer to particle diameter or equivalent diameter. These particles include liquid droplets, regular or irregular shaped crystals, or aggregates of odd shape. Particles are often classified by size. For example, the particles having diameter less than or up to 10 micrometers are known as PM10, and particles having diameter up to 2.5 micrometers are known as PM2.5. Their chemical composition may also vary. They could be dilute water solutions of acids or bases, or they could be some salts, organic liquids, or materials present in the earth's crust such as dust. They could also be unburnt carbon, that is soot, and toxic metals. The visual appearance of dust, smoke and haze is determined by their optical properties, which include light extinction, scattering and absorption. Physical and chemical properties of ambient particulate matter are used to determine their optical properties. Particles produced by any particulate matter source have specific physical, chemical and optical properties. So particulate matter can actually be viewed as several pollutants rolled into one, since every type of aerosol has its unique properties and sources, and their control measures are also different. The effects of particulate matter can be far-reaching. There could be some beneficial effects, such as they also form cloud and fog. They could also help balance the temperature of the atmosphere on Earth through light reflection. They can also form nuclei for the formation of ice crystals and water droplets. They also provide a surface for many atmospheric reactions such as neutralization, oxidation, etc. Photochemical oxidations can also take place on the surface of particulate matter. Particulate matter is responsible, on the other hand, for having adverse effects on human health, especially fine particles such as PM10 and PM2.5, which enter the human body through the respiratory tract. These particles are called respirable particulate matter, or RPM. PM10, when inhaled, penetrates deep into the lungs, bypassing the body's respiratory filters, and can give rise to chronic respiratory diseases such as bronchitis, bronchial asthma, pulmonary edema, etc. Particulate matter 2.5 is even more dangerous than particulate matter 10 because they can affect the exchange of gases inside the lungs by reaching the peripheral regions of the bronchioles when inhaled. Air pollution due to particulate matter is recognized by WHO to be responsible for diseases such as chronic obstructive pulmonary disease, or COPD as it is called, and lung cancer, in addition to infections of the respiratory system. This happens because bacteria can thrive well on solid particles. The removal of particulate matter from exhaust gases is an important strategy for the air pollution control authorities. Let us now talk about the ions and radicals present in the atmosphere. The upper layer of the atmosphere, as we have already said, is known as ionosphere, starting from the mesosphere onwards, because it contains significant number of electrons and positive ions. The positive ions could be the oxygen molecule ion, atomic oxygen ion, nitrosyl ion, etc. They persist for long durations without recombining to give neutral species because their rarefied conditions exist in the upper atmosphere. In the ionosphere, the ions are primarily produced by ultraviolet light. At night, when there is no ultraviolet light, the positive ions present in the atmosphere combine with free electrons, and this results in the formation of original neutral species. The upper layer of atmosphere is strongly influenced by the magnetic field of the Earth. The best known example of this phenomenon is the Van Allen belts, which are two concentric circles of charged particles surrounding the Earth. The belt, inner belt and outer belt are for protons and electrons respectively. The Van Allen belts were discovered in 1958, and they exist as two concentric belts like forming a donut kind around the earth, with the earth's magnetic axis projecting through the center hole of the donut. In the troposphere, ions are also produced during precipitation by the shearing of water droplets. While the rainwater comes down, this shearing may be caused by the compression of descending masses of cold air or by strong winds over hot, dry land masses. The electromagnetic radiation in the atmosphere, which are high in energy, may also produce free radicals, which are atoms or groups of atoms with unpaired electrons. Free radicals are very reactive. The half-lives of radicals at high altitudes may be of several minutes or longer than that. Radicals are used in chain reactions, which at least one of the products then formed is a free radical again. Finally, the chain may be terminated by the combination of two free radicals. Some such reactions, for example, are RH, an aliphatic hydrocarbon, combining with the oxygen radical to give a peroxo radical plus a hydroxyl radical. Then further, there are organic compounds such as acetone or acetaldehyde, which then absorb radiation and become radicals such as the methyl radical and CHO radical. The two methyl radicals may recombine to have a chain termination reaction and give the hydrocarbon back. Free radicals contribute in the formation of photochemical smog. Hydroxyl radicals in the atmosphere are also a very important species. They are the product of reaction between water present in the atmosphere and excited oxygen atom, which are formed by photodissociation of ozone present in the atmosphere. In the troposphere, hydrogen and hydroperoxy radicals are produced by a number of reactions, and the sequence is somewhat like this. A hydroxyl radical can be combining with carbon monoxide, which is present due to insufficient burning of fuels, and this gives rise to carbon dioxide and atomic hydrogen. The hydroxyl radical can also combine with atomic oxygen to give molecular oxygen and another hydrogen ion. The hydroxyl radical may also combine with atomic oxygen in the presence of a third body, which is denoted as M sometimes. This could be a nitrogen molecule, and this imparts translational energy to the molecule and will give a hydroperoxy radical. A hydroxyl radical may also combine with ozone to give oxygen, molecular oxygen, and a hydroperoxy radical. Hydrogen atom may combine with oxygen atom in the presence of a third body to absorb the energy to give hydroperoxyl radical as well. So a large number of radicals and atoms can be produced rapidly by these reactions. These species are fundamental to the chemistry of the atmosphere in the gas phase. Since these species are highly reactive, their concentration is very low in the atmosphere. Their typical atmospheric concentration are like this: hydroxyl radical 7 into 10 to the power 5 per cubic centimeter of air, and hydroperoxy radical 2 into 10 to the power 7 per cubic centimeter of air. So high reactivity ensures that they have short residence time. The hydroxyl radical resides in the atmosphere for less than 1 second, while that of the hydroperoxyl radical lifetime is around 1 minute. Atmospheric trace gases such as hydrogen sulfide react with these radicals. The sulfur gases are biologically produced in the atmosphere in the form of sulfides. These could be hydrogen sulfide, dimethyl sulfide, and carbon disulfide. They react with highly reactive hydroxyl radical and give CH3SOH, CH3SO3H, etc. The above reaction produces methyl sulfonic acid, and most of the product results in the Earth's atmosphere. Small amount gets oxidized through sulfur dioxide. Hydrogen sulfide reacts with hydroxyl radical to give hydrogen sulfide radical and water. The product so formed is oxidized in turn by sulfur dioxide through a number of reactions, and finally sulfuric acid can be formed. Carbon disulfide, the final product of oxidation by hydroxyl radical for this is in the formation of carbonyl sulfide and sulfur dioxide in equal proportions. The reaction of carbon disulfide with oxygen atoms in the atmosphere is more important than its reaction with the hydroxyl radical. Reaction with carbon monoxide, for hydroxyl radical, we get carbon dioxide and atomic hydrogen. Formaldehyde can react with hydroxyl radical to give HCO and water. Methane can react with hydroxyl radical to give methyl radical and water. Methyl radical so formed is then converted into CH3O2 by the reaction CH3, the methyl radical, oxygen and a third body collision. So we get CH3O2 and the third body which can gain some translational energy from this. This can then further react with the hydroperoxy radical. CH3O2 plus hydroperoxy radical will give a radical CH3COOH and molecular oxygen. Hydroxyl radical and hydroperoxy radical can also react with each other. Two hydroxyl radicals react in the presence of a third body to give H2O2, and two hydroperoxide radicals react in the presence of a third body again to give H2O2. H2O2 is soluble in water and it is a strong oxidizing agent. In the atmosphere, hydrogen peroxide plays an important role in oxidation processes. So to summarize this unit, we've got to know that the atmosphere is the blanket of gases surrounding a planet, and in case of the Earth, this blanket of gases is made up of air. Atmosphere is also a segment of the environment, and there are many layers in the atmosphere like troposphere, stratosphere, mesosphere and thermosphere. Earth's atmosphere, as we already said, is made up of air. Air is a mixture of gases. The major components of air are nitrogen and oxygen. There are some minor constituents such as argon and some which are trace constituents, which are the other noble gases and carbon dioxide. This is, we are talking so far about dry air. There could also be wet air in which there is water vapor. Water vapor, of course, is not present in the same amount all over the globe, and it varies from 0 to 2%. Particulate matter is responsible, on the other hand, for having adverse effects on human health, especially fine particles such as PM10 and PM2.5, which enter the human body through the respiratory tract. These particles are called respirable particulate matter, or RPM. PM10, when inhaled, penetrates deep into the lungs, bypassing the body's respiratory filters, and can give rise to chronic respiratory diseases. Particulate matter 2.5 is even more dangerous than particulate matter 10 because they can affect the exchange of gases inside the lungs by reaching the peripheral regions of the bronchioles when inhaled. Air pollution due to particulate matter is recognized by WHO to be responsible for diseases such as chronic obstructive pulmonary disease, or COPD as it is called, and lung cancer, in addition to infections of the respiratory system. This happens because bacteria can thrive well on solid particles. The removal of particulate matter from exhaust gases is an important strategy for the air pollution control authorities. The atmospheric composition is something which affects the climate of the earth, and environment, since is affected by atmospheric composition is important and is the responsibility of everyone to maintain the atmospheric composition in its natural form.